Let's talk about acceleration of a moving object. We know that the velocity vector is simply the first derivative of our position vector function. So if we're representing our position as we move along a curve using a vector function like r of t, then r prime would give us velocity. We also know that the unit tangent vector can be calculated using the first derivative of our position function, r, and dividing off by its magnitude. With these two facts, we can create the following statement that says the velocity vector is equal to the magnitude of the first derivative of our position vector times the unit tangent vector. And because we know that the magnitude of the first derivative of our position vector is the same thing as the speed function, remember this v of t is a scalar function which represents speed, then we know that velocity can be represented as speed times the unit tangent vector. We can use this to find acceleration simply by taking the derivative of both sides of this equation. On the left, we would have the derivative of velocity, which is acceleration. On the right, we need to use the scalar product rule because we have a scalar function, v of t, times a vector function, the unit tangent vector. Applying that scalar product rule, we get v prime times the unit tangent plus v times the derivative of the unit tangent. And this is one way to write acceleration. But there's a few substitutions that we can make to make this easier on us to use multiple times. So we know that the principal unit normal is just the first derivative of the unit tangent and then normalized. So that means we can replace the unit tangent derivative with the magnitude of the unit tangent derivative times the principal unit normal. So we're going to take this t prime out and replace it with the magnitude of t prime times the principal unit normal. We also know that kappa, that's our curvature constant, can be calculated using the magnitude of t prime divided by the magnitude of r prime, which means we could then replace that t prime magnitude with kappa times magnitude r prime, or better yet, with kappa times magnitude v of t, that speed vector. So we're replacing the magnitude of t prime with kappa v of t, or kappa speed. And then we can clean that up a little bit to write that as kappa times v of t squared, since there was a v of t factor here, and now there's another one here. So it's like we have a square. So acceleration has two components. We have the tangential component and the normal component. Sometimes the normal component of acceleration is also called the radial component, and that has to do with the circle of curvature. If we look at this drawing in the bottom left of the screen, we can see that there is a vector AR. That's actually the principal normal vector pointing into the oscillating circle of curvature. Because this is something that we need to use to calculate acceleration in the moving frame, we've come up with ways to represent these coefficients. Notice that v prime of t, this is the first derivative of the speed function, that's a scalar. Also, kappa times v of t squared is another scalar. The unit tangent and the unit normal are the only two vectors in this vector equation. So we represent those two coefficients using a of t, that's the tangential acceleration coefficient, and a of n, that's the normal or radial acceleration coefficient. Let's go through an example of how to represent acceleration in the moving frame. Now, this a acceleration vector is specifically tied to the t and b frame. And we can see that we're using t and n here. In the standard Cartesian rectangular coordinate plane, instead of t and n as our unit vectors, remember that we use I hat, j hat, and k hat. So it's very similar. We're writing a linear combination of acceleration using the unit vectors, unit tangent, and unit normal. So if we wanted to represent acceleration this way, we would need to calculate the a of t coefficient as well as the a of n coefficient. So that's the tangential and normal components of acceleration. And to do that, we're going to use these shortcut formulas. It says for the tangential acceleration, we need to calculate the velocity vector and the acceleration vector. Both of these are going to be calculated in the fixed frame, not in the t and b frame. So let's start by finding v, the velocity vector, which is simply the first derivative of our position vector. And if we're looking at a position vector like t squared I hat, 2t minus 3, and j hat, 3t squared minus 3t k hat, our first derivative would look like 2t, 2, 6t minus 3. And then acceleration would be the second derivative. So that would look like 2, 0, 6. And then dot those two together. We would get 4t plus 0 plus 36t minus 18, or 40t minus 18. We also need to find the magnitude of v of t. So let's calculate magnitude of v. Take each component and square it, add them up, and square root them. All right, we have everything we need now to write the tangential coefficient of acceleration. It's the dot product v dot a, which we found to be 40t minus 18, divided by the magnitude of the velocity vector, which we found was the square root of 40t squared minus 36t plus 13. So it's kind of one of those plug and chug ideas. We also need to find the normal component. There's a typo here, ignore those vector arrows. We need to find the normal component of acceleration using the formula that we see here, which requires us to know the tangential component of acceleration. So we need the magnitude of our acceleration vector squared. So let's go ahead and calculate that. It's going to look like 2 squared plus 0 squared plus 6 squared. And I can write square root, but I'm going to square it because we need magnitude of acceleration squared, so might as well not even write it. That's going to come out to be 4 plus 36, or 40. And then I need the tangential component of acceleration squared. I'm not going to work that out, I'm just going to write it into the formula. So for an, the normal component of acceleration, we will have 40 minus the tangential component, so that's 40t minus 18, 40t squared minus 36t plus 13, that whole term squared, and this is all being square rooted. And we could do some algebra here to simplify this, but there's not really a big point to that right now. So just for the sake of exposure, I wanted to show you what these look like, but I don't want to go through the algebra exercises. All right, part B to this problem says that we want to find them at t equals 2. And this wording doesn't make sense. We want to find at and an when t equals 2. So all that would mean is plug 2 into each one of these coefficients here so that you could calculate them. At with t equals 2 plugged into it. That's going to come out to be 62 over root 101. And then AN with 2 plugged into it, that's going to come out to be 14 over root 101. And again, this is just to give you some exposure. We're not going to spend a whole lot of time talking about acceleration in the moving frame, but since we learned what the T and B frame was, that's probably worth talking about, at least for a few moments.